Hi everyone, my name is Shilin and I'm here to present my final project for 15463. In this project, I try to implement the method presented in Computational Periscopy with an ordinary digital camera by Charles Saunders, John Murray Bruce, and Vivek Goyal. I also did some experiments with recovering a 2D hidden scene as well. So without further ado, let's get right into it. First, I want to tell you a little bit about what computational periscopy means. Unlike a regular periscopy, the computational periscopy uses a diffuse wall as a mirror to give insight of a hidden scene. As shown in the middle figure here, in the setup of this paper, a monitor is placed out of the line of sight of the camera and displays the scene. In this case, it is a mushroom man. The camera is pointed at the diffuse wall, and light from the monitor passes around an occluder, hits the wall, and finally bounces into the camera. This brings us to the key insight of this paper, which is the use of an occluder. It helps make the light transport matrix better conditioned, which means that its inverse can be computed with better accuracy. If you recall that each column of the light transport matrix roughly represents the scene under a given light configuration, then this makes intuitive sense because the inclusion of an occluder would make the columns of the light transport matrix more different from each other. With this in mind, the algorithm can be split into three stages. First, we divide the figure into 3 channels, and then we estimate an occluder position for each of the channels. We take the average of the 3 as the final estimated occluder position, and we use that to compute the estimated light transport matrix. Using that matrix, we are able to reconstruct the scene. Next, I will talk in more details about what each stage of the pipeline looks like and show the relevant results that I obtained. I will actually start with estimating the light transport matrix because estimating the occluder position makes use of that. The first equation here represents the gradients at a point on the wall. So the point would be PW, and X is in the hidden scene that we are trying to estimate or reconstruct. So the cosine angle term here represents just the angle between PW minus X and the normal at X, and similarly for the other cosine term. The V term here is the visibility, so it represents whether or not X and PW can see each other given the position of the occluder P0. And mu here is a radiometric model of the monitor that is viewing angle dependent, and F is the thing that we're trying to reconstruct, and B here represents sort of the ambient irradiance that can be seen at PW, but is not part of the hidden scene. And so through some discretization, for example, the first one we discretize over pixels in the camera space, and in the second one here we discretize the scene into pixels as well. We can arrive at this equation by setting the residual term to be B, and then this A matrix multiplied by F plus B would give you the image that we are capturing with the camera. And so to further estimate this integral as a sum of piecewise linear components, we can write it using L samples down below, and that's the last equation. And if you are able to implement this equation, you can have an estimate of the light transport matrix given the occluder position P0. And here is the light transport matrix that I got from the data in the paper. So next, I will talk about how to estimate the occluder position. Before we can talk about that, we need to discuss what is a computational field of view. So on the left here is a really nice diagram that visualizes this. So the computational field of view is a part of the scene that are visible to a part of the camera's field of view, but occluded from another part of the camera's field of view. And so within this computational field of view, we also have something called the best conditioned region, where all four edges of the occluder falls within the camera's field of view, so region C here. And so if we return to the light transformed matrix that was recovered, then we can produce mosaic plots like this. So the example here shows that if we take sort of this one of the first few columns and then reshape it to match the shape of the image captured by the camera, then it would look something like this. So here is the shape of the projection of the occluder here. And so what this diagram shows that is that the last two rows in this mosaic plot are not within the best conditioned region. And so I guess just to further clarify, each figure here shows what the wall would look like if only the grid with the corresponding index on the monitor is emitting light. And so with that in mind, we can see here is a diagram of what would happen if we shift the occluder position. So the first one shows what happens if we shift the occluder position along the x-axis. The second one is for the y-axis, and the third one is for the z-axis. And so in order to find the estimated position of the occluder, we find the occluder position that maximizes a times the pseudo-inverse of a y norm. So that's the equation. Given that it takes roughly 3 minutes for me to compute a light transform matrix, I was not able to do this part of the algorithm, just simply due to the time constraint. And so next I will talk about how to reconstruct the scene with a estimated light transform matrix. So the authors noted two important properties for a real-world scene. So the first is that the gradient of a real-world image is rather sparse, and so we can take advantage of that by adding a total variance or TV regularization on top of our optimization problem. And the second insight is that the real-world scenes have slow spatial variations of ambient light. And so if we take the difference of two adjacent pixels, then that would help us cancel out the background term that's just hanging out there. And so finally, combining these two, the authors decided to solve this optimization problem where the scene is reconstructed as the one that minimizes this equation, and D here is the so-called difference matrix. And so next I will show some of the reconstruction results that I have obtained. So it was difficult to find in an optimized package that has the exact regularized form as the one that was just shown on the last slide. And so I tried both just the very simple least squared optimization and some other slightly differently formulated TV regularization. The results, as you can see, are not very good. So first I will talk about the difference between the least squares optimization and the TV regularization. I think the TV regularization is really doing its job here, and the reconstructed results look much more block-like or have few sparser gradient than the least squares reconstruction results. I think what is contributing to the error here is that I probably have the wrong correct position of the occluder. But as I mentioned earlier, I was not able to really run the algorithm and estimate that. Instead, I got the numbers from the source code that was released alongside the paper, and I think I may have misinterpreted that. So with that in mind, I still wanted to be able to reconstruct some sort of hidden thing, so I came up with this set of experiments. So here is the setup. The camera is again pointing to a white diffuse surface, and the monitor is set up such that the camera has no direct line of sight of what's displayed on the monitor. And I did two sets of captures, one where there is an occluder present and one where there is not. And so the experiment sort of goes in two stages. In the first stage, I try to build the light transform matrix from the images captured from individually lit grid. So I have 9 patterns that look like this. So I have a 3x3 grid here, and the borders are always going to be black, so that when the picture is displayed on full screen, the lidded grids have equal size width and height. And so after capturing 9 things like this, I also capture an oblique thing to be able to better illuminate the ambient lighting. And after that, I capture the hidden things, like the one that's shown here, and try to reconstruct the results from the light transform matrix that I obtained in the first stage. And the reconstruction algorithm is also painfully simple. I iterate through all 2 to the 9th possible configuration of the 3x3 grid and find the one that produces the least squared distance reconstruction from the actual captured image. And so I then return the top 5 results, and the next slide shows what I got. So the first rows in each set here is a reconstruction with an occluder present, and the second row is a reconstruction without an occluder. As you can see that in all 4 of the examples, the reconstruction without an occluder was able to reproduce the actual hidden thing as a top result, so the one with the minimum squared distance from the actual captured image, whereas the reconstruction with an occluder struggled a little bit more. I believe that this is because the inclusion of an occluder makes the scene a lot more complicated, and perhaps I needed more images to be able to to be able to have a better reconstruction with that. And that is all I have. Here are some of the references. So the first one is simply the paper that I have been referencing throughout the presentation, and the second one is a tutorial for doing TV regularization using the PyLops package. And finally, thank you so much for your time and attention.